In the previous module, you learned that formation of tetrahedral and octahedral voids takes place when the constituent particles are arranged in a cubic close packing or hexagonal close pack. You also know that in a close packing, the number of octahedral voids formed is the same as the number of spheres or the constituent particles, while the number of tetrahedral voids is double the number of spheres. Let us now look at how the cations and the anions are placed in the close packing. Usually, the anions being larger in size form the basic crystal lattice, and the cations being smaller in size occupy the voids. A relatively small cation occupies the tetrahedral void, while a relatively bigger cation occupies the octahedral void. For example, sodium ions having size of 102 picometers occupy the octahedral voids in a sodium chloride lattice, and the zinc ions with size of 74 picometers occupy the tetrahedral voids in a zinc sulfide lattice. The fraction of octahedral or tetrahedral voids occupied in a given lattice depends upon the chemical formula of the compound. To have a better understanding of the concept, let us work on a few problems. In corundum, the oxide ions form the hexagonal close packing lattice, and the aluminium ions occupy 2/3 of the octahedral voids. What is the formula of the compound corundum? You already know that the number of octahedral sites in a cubic close packing is the same as the number of constituent particles. Now, if N oxide ions form the crystalline lattice, so the number of available octahedral sites is also N. But only 2/3 of N octahedral sites are occupied by the aluminium ions. This implies that the ratio of aluminium ions to the oxide ions in the lattice is 2/3:1. Thus, the whole number ratio of aluminium ions to the oxide ions is 2:3. The formula of corundum therefore becomes Al2O3. Let us solve one more problem. In a crystalline solid, anions B are arranged in a cubic close packing, and the cations A occupy 50% of the tetrahedral voids and 50% of the octahedral voids. What is the formula of the compound? Now, anions B are arranged in cubic close packing. If N is the number of anions B, then the number of available tetrahedral voids is equal to 2N, and the number of available octahedral voids is N. Cations A occupy 50% of the octahedral voids. That is, cations A are present in N/2 octahedral voids. Also, cations A occupy 50% of the tetrahedral voids. That is, cations A are present in 2N/2 tetrahedral voids. The A:B ratio thus becomes 3N/2:N. The simple whole number ratio of A:B is 3:2. Thus, the formula becomes A3B2. Now let us try to locate the tetrahedral and the octahedral voids in the CCP or FCC structure. Consider a CCP or FCC unit cell. Subdivide this big cube into 8 small cubes as shown here. Now consider one small cube. A careful look shows that spheres are present at the alternate corners in this cube. When these spheres are joined, we get a tetrahedron, and the void thus generated is a tetrahedral void. As each small cube has one tetrahedral void, there are a total of 8 tetrahedral voids in a CCP or FCC unit cell. Also, you know that in a CCP or FCC unit cell, 4 atoms or ions are present per unit cell. Thus, the number of tetrahedral voids is 2 multiplied by 4. That is 8. Let us now locate an octahedral void in the CCP or FCC unit cell. A look at the body center of this unit cell shows that it is surrounded by 6 spheres at the center of each face. If we join these 6 spheres, we get an octahedron, and the void thus formed is an octahedral void. This octahedral void is not shared by any other unit cell and contributes fully to this unit. Further, octahedral voids are also present at the center of each edge. As you can see, each edge is shared by a total of 4 unit cells. It therefore contributes only 1/4 to each unit cell. Thus, the total number of octahedral voids present per unit cell comes out to be 4. This is same as the number of atoms or ions present in a CCP or FCC unit cell.